All right, so this is 15.7, part 2, which is the second derivative test. So the first thing is, this is a direct analogy to the first derivative test. A second derivative test in one variable calculus, so we should write that down first. So one variable. If we have f of x is our function, and we know f prime at a point, let's say a, is equal to 0, then what you can do is you can analyze the behavior of your function, whether it's a local max or min, by looking at the second derivative. And essentially, that makes sense because if your tangent line is horizontal right here and f prime prime is positive, then you know it's concave up, right? So essentially, in terms of the picture at least, the idea is f prime prime bigger than 0 means concave up, and f prime prime less than 0 means concave down. Okay, so if f prime at a is 0, which means you have a tangent horizontal line, and your f prime prime is positive, to be concave up, you have to look something like that, right? And if you're concave down, then you have to look something like this. Again, when your tangent line is horizontal. So that tells you information about, whether your function is function has a local max or min, right? So f double prime bigger than 0, concave up, which means you have a local min. Oops. Right? Local min. And this means when you're concave down, you have a local max. Okay? Very importantly, if f double prime is equal to 0, then we don't know, because you can have all the situations, all the different situations when it's 0, right? So for example, f of x equals x to the 4th. This is f prime at 0 is equal to 0. F double prime at 0 is equal to 0. This is a min, right? F of x equals negative of that. You're going to have f prime of 0, 0. F double prime of 0 equals 0. You have a max, right? F of x equals x cubed. F prime equals 0. F double prime equals 0. You have neither. All right. So of course there is the situations where the second derivative test fails. All right. So in two variables, things are, of course, a little more complicated because you have more than one direction to be thinking about, whether you're concave up or down. But essentially, the idea is the same, at least in terms of the picture. If you have a flat tangent plane, so let me write down f of x comma y. If you have a flat tangent plane, in other words, gradient f at, let's say, a comma b is equal to 0, that means you're, at this point, you have a flat tangent plane. Now, if I, let's say, look in this direction and it turns out I'm concave up, right, then I'm going to look like that, right? I have to look like that. Again, just in terms of the one variable calculus where you're thinking of the function as just a one variable function over this line segment. Okay. Now, the deal is if this happens to be the case for every single direction, right, let's say, let me just draw one other one. Let's say this direction, it's also concave up, like that, right? You can kind of see that if this is the case in every direction, that it's always concave up, the one variable version in the direction, given by the red and the blue arrows, and every other direction, then you're going to be a local min, right? In short, if all the kind of one variable function, one variable kind of version of this f of x comma y, along every direction is concave up, then you're a local min, right? If it's all concave down, then you're a local max, okay? Sounds simple, and it sounds like maybe that would be the, something like that would be the second derivative test, but as it turns out, things are a little bit more complicated. So let me write down what the second derivative test is. what it actually is, or at least the version that we'll see in almost every calculus book. We'll talk about why it's so terrible, and then we'll kind of discuss it the way it should be discussed. But for that, you're going to have to know a little bit of linear algebra. So if you know linear algebra, then you're all fine. If you haven't taken linear algebra, maybe refer to this when you do take linear algebra, perhaps your next calculus sequence class. It's definitely worth it because it's a great kind of example of calculus and linear algebra interacting together in a very important way. Okay, hopefully if you do take a linear algebra in your linear algebra class, they will explain this as a tiny mini section, but sometimes they don't. Okay, so let me explain it at least the way the book does it. And again, almost every calculus book does it, so it's not just ours that's particularly bad. So second derivative test. And again, all the usual caveats. Your function f has to be differentiable. In fact, it has to have two derivatives. It has to be second differentiable at the point of interest, right? But we're not gonna worry about that too much in our class as usual. All right. Okay. Second derivative test. And again, I'm just gonna. Well, you'll notice in the book they only focus on the two variable version because the way they describe it, they cannot do a three variable version. And the way I'm going to kind of do it in the correct way, it'll be very natural how to extend it to three variables, four variables, and so on. Okay, which is why I hate this version of the second derivative test that they teach in multivariable, that we teach in multivariable. Okay, so we have a two-variable function, function, gradient f equals 0 at AB. Gradient f equals 0 at AB. All right, so the second derivative test says, so in particular, of course, like we said last time and before, that means f sub x AB equals 0 and f sub y AB equals 0, right? Okay, in any case, second derivative test says that you have to look at the quantity fxx times fyy minus fxy squared. And I'm going to kind of do it like this. Evaluate it at AB, evaluated at AB, evaluated at AB. Okay, everything is evaluated at our point of interest. All right. But I think if I just stick in all these ABs, things will look kind of really, really messy. So essentially, fxx, fyy minus fxy squared. Okay. So you consider this quantity. If this is, so we're going to have three situations, bigger than 0, we're going to have less than 0, and we're going to have equal to 0. All right. Okay, if this is bigger than 0, there's going to be two cases, fxx bigger than 0 and fxx less than 0. So this is going to be local min. All right, this is going to be local max. Okay, so if this quantity, this special quantity here, which we'll describe very, very easily in terms of linear algebra, if this thing is positive and fxx, so let me emphasize this with and, this one is and fxx is positive, then you have a local min. All right. If this quantity is bigger than 0 and fxx is less than 0, then you have a local max. All right. Okay, number 2, and we'll talk about some of the issues here. Number 2, if you're less than 0, if this special quantity is less than 0, this is a saddle point. All right. So again, in terms of the picture, it looks something like in some directions it's going upwards, but in other directions it's going down. All right. You can that's essentially almost a technical definition for a saddle point, but if you do want to kind of be very mathematical, you can take a look at the book and they'll have a nice kind of more formal definition of a saddle point. Essentially, it's a point where gradient f is 0, and in certain directions, if you take the one variable derivative, it's negative, and in other directions, it's actually positive. Okay. All right. And number 3, if it's equal to 0, then we don't know. Could be max, could be min, could be saddle. All right. Okay, so that's it. That's the second derivative test. And from here, if we just leave it like this, you can use this, for example, on the homework or whatever. Just have to remember, the kind of algorithm here. Now, a couple issues. So first of all, you'll see it's very, very clunky. The fact that you have to look at this quantity up here that's not a problem. That's a very natural quantity to be looking at, and we'll discuss that. But this in this kind of number 1 part where this quantity is bigger than 0, breaking it up into 2 portions where f(x(x) is bigger than 0 and f(x(x) is less than 0, it's very, very clunky. And it's very, very unnatural, because one question you might ask is, why is f(x(x) so special, right? Why doesn't it say fyy is bigger than 0 or fyy is less than 0? What about f(x(x) equal to 0? Why is that not part of this, part of the possibilities? Well, the deal is you can actually look at fyy alternatively instead of f(x(x), and you could just replace the whole thing with fyy bigger than 0, local min, fyy less than 0, local max. All right. So already it's kind of unsatisfactory because we've kind of arbitrarily chosen the x's instead of the y's. Okay, number 2, why isn't there f(x(x) equal to 0 as a possibility? Well, the deal is this special quantity here, f(x(x) fyy minus fxy squared. If that thing is bigger than 0, then of course, not of course, but, well, I guess of course. Of course, you can't have f(x(x) equal to 0, because if f(x(x) is equal to 0, then the first term here is going to be 0, and the second term is minus of fxy squared, and that can never be strictly positive, right? So that's why there's no f(x(x) equal to 0 term. Okay. All right. In any case, that's our second derivative test. And I guess I should do an example. So, oh, by the way, so one thing that is kind of nice in the second derivative test is you can recognize the saddle conclusively if this quantity is less than 0, right? In contrast to the one variable version where f prime, the equivalent of the saddle would be something like f of x equals x cubed, but you can't recognize that with the second derivative test. Okay, so let's do one example. So f of x comma y, but it's very straightforward. Equals x squared minus y squared, right? So gradient f is equal to 2xi plus 2yj. Gradient f is equal to 0 when x equals 0, y equals 0, right? So the point of interest, the only point of interest where we can talk about is 0 comma 0. All right, but again, you can use this second derivative test at any critical point or any point where gradient f is 0, and you better not be using it where gradient f is not 0. All right, just like in one variable calculus. Okay, so let's look at our special quantity, f(x(x), fyy minus fxy squared. So f(x(x), so this is all going on at 0, 0, at 0, 0, at 0, 0, at our point of interest. So, we actually get a number. So f(x(x) at 0, 0, f(x(x) is, so gradient f is 2x, f(x(x) is just going to be 2. fyy is going to be 2. And then no matter what, at any point actually, fxy is going to be 0, right? So this is going to be equal to 4. So that's bigger than 0. fxx was equal to 2. Oops, sorry, I'm doing the minus, right? Sorry, I'm doing x squared minus y squared. So fyy, so this is, sorry about this. This is a minus sign right here. Again, because I'm doing x squared minus y squared, so that should be a minus sign. So fyy should be minus 2. So this should be minus 4, which is less than 0. Okay, so that means it's a saddle point. So instantly, we've realized that this guy's a saddle point. All right. Okay, so this is a nice, just a nice simple example of the second derivative test. Again, normally if you have a more complicated function, your second derivatives are obviously going to be more complicated than just constants, right, as in this example. But of course, it depends on completely on how complex your function is. Okay, so I said in part 1 of this lecture that for the kind of just the regular optimization problems in this section, I don't think you should be using the second derivative test. It doesn't really give you much because you're going to have to plug in anyway. So there's no reason to actually go through all the work of doing the second derivative test. However, it is super useful in real life in terms of analyzing functions that you don't actually have the formulas for. So if you want to do some sort of optimization-like problem, you can't actually solve anything because you don't have the formula, right? You only have information about f. In particular, perhaps you know information about derivatives of f or something like that. And so in those cases, something like the second derivative test is super important, actually. But for our class, right, we're not doing this kind of more hardcore analysis, right? We're working mostly with just concrete functions, f of x comma y equals, right, sine x times cosine x or something like that. But when you do get to kind of more serious ODEs or ordinary differential equations or partial differential equations especially, this kind of analysis is super important, the kind that we get from here. Actually, let me do a really quick aside where I show that something like the idea behind this second derivative test can be really important, just as kind of motivation, because it seems like, you know, I don't want people to walk out of the class saying it's completely worthless because in optimization we never used it. So here's a really quick. Let me do a one variable version of the idea, but you can imagine how this might expand to multivariables. So just a very quick aside. So imagine I have a differential equation. Let's again just stick to one variable calculus. So I'm thinking about functions f of x, and let's say I'm trying to solve this equation, f double prime plus lambda f equals 0, right? F of x. So this is a differential equation because, well, what is a differential equation? Differential equation is a equation where you're trying to find a function given information about its derivatives, essentially. All right. So integration is in a way a differential equation, but it's so simple that we call it something else. So this example here is a more typical differential equation, right? As opposed to, right, like I said, if it's just something that you give me information about the derivative and I give you the function, well, literally then f prime equals sine x is a differential equation, but that's just too silly, right? Too easy. Okay, so this is a more serious, interesting, important, actually, this differential equation here. Okay, so how do we kind of use the second derivative test in a way to analyze this guy? So let's say lambda here is lambda is a constant. Okay, and let's say lambda is less than 0. Okay, let's try to analyze this. Let's pretend we don't know how to solve this. So our goal is to either maybe solve it or try to find information about f if we can't solve it. Okay, so here's what I'm going to do. I'm going to say, okay, at a positive maximum of f. So in other words, here's the x-axis, here's the y-axis. If my function f, the actual solution to this problem, has a maximum and it happens to be positive, all right, then what are we going to know? Let's see. Well, because it's a maximum, And we know that it's concave down at this point of interest, right? Let me give this maximum a name. Let me call it x equals a. Okay. Then we know f prime prime at a is negative. This is pretty much the second derivative test. All right. Again, we only know it's less than or equal to 0, but let's pretend it's just less than 0, right? If you do the serious analysis of this, the equal 0, you can take care of that case. But that's going way too far off track. So let's just pretend f double prime is less than 0, okay? Actually, we don't even need to, in this particular case, actually, now that I think about it, we can actually do that. We don't have to split, we don't have to kind of cheat. All right, so we know this, right? This is essentially the second derivative test, okay? So we know f prime prime of a is less than 0. Well, that's the first term here. What's the second term? Second term is lambda f of x, right? Well, we know lambda is less than 0, right? So lambda f of x, f of a, we're at a positive maximum. So f of a is positive. Lambda is negative. All right? So this whole term is negative. All right? Negative, strictly negative. Okay? And so f prime prime of a plus lambda f of a cannot be 0. All right? And so what does that mean? That means that any f that solves this differential equation right, no matter what lambda is, as long as it's less than 0, has no positive maximum. All right, so its graph, when you look at anything that satisfies this, we've concluded at this point, it cannot have a top of a hill above the x-axis. Okay. All right, on the other hand, what about negative min? At a negative min, let's say x equals b, what do we know? We know f double prime of b, so a negative min, so it would be a minimum, underneath the y-axis, underneath the x-axis. We know that f double prime has to be bigger than 0. So that's essentially the second derivative test, right? Lambda f of b, lambda is negative, right? And f of b, we're at a negative min, and so this is negative, so the whole thing is positive. This guy's lambda f of b is positive. So f double prime of b plus lambda f of b has to be positive, right? In fact, it cannot be 0. Okay? So any f that solves this differential equation has no negative min. All right. Okay, now, if you think about this, let's say we are looking again at this differential equation, plus lambda f, lambda equals 0. Lambda is bigger than 0. Oh, sorry, less than 0. Right? So for example, lambda could be minus 1. All right, just to be, kind of simple. Let's say we're solving this where f on just an interval. Interval, let's say from 0 to 2 pi. All right. So let's say we're solving this on the interval 0 to 2 pi, and let's say we're only interested in functions f, where f of 0 is equal to f of 2 pi is equal to 0, periodic functions. All right. If you've done some physics, you'll probably have recognized this already, and the fact that we're kind of forcing our function to be 0 at 0 and 2 pi essentially tells us we're looking, and this differential equation, something like this, tells me we're probably wanting to think about waves or something like that. But what happens is, if you do think about this situation, you'll notice that, well, if we do have a solution, then it's going to have to be super simple, right? Because it can't have a positive max. So for it to have a maximum, the maximum has to be underneath the x-axis, right? But if it has a maximum underneath the x-axis, it's going to have a minimum. It's got to have a minimum underneath the x-axis as well, right? But we can't have that, right? So what does that mean? That means there is no max and mins. So it means the only solution to this problem is f equals 0. All right. So without calculating kind of with a concrete function or anything, just looking at a specific form of a differential equation, I have concluded that essentially in this setup, there's no interesting solution to this problem. All right. And again, all I'm using is the second derivative test. Now, for the multivariable version, we could do the same exact analysis except with more complex setups, right? So in that case, we would be looking at f double prime would become the Laplacian, if you've seen that, right? Lambda f, you could solve this situation, and you can do literally the same analysis and understand something about what could be a very, very complex situation, right? F of x comma y, f of x comma y, right? You can analyze this and immediately you know there's no solutions. All right, so that's really the power of the second derivative test. But again, we're not doing this kind of analysis, but remember this for maybe next your next class in ODEs, or perhaps something like this maybe in the class after that, the ODE class, maybe your second ODE class perhaps. Okay. Oh, by the way, if lambda is bigger than 0, there certainly are solutions to this, because sine nx would satisfy the conditions of the being fixed at 0 and 2 pi, and it would sine nx prime prime would be n squared sine nx, and so negative of that, and so you could actually solve the equation. Okay, so that's some motivation at least. Now let me talk about how to really discuss the second derivative test. So we're going to be using a little bit of linear algebra, but the first part of this everybody can understand, and it's a good discussion because we're going to be talking about again converting our second two-variable problem into multivariables, which is always something that you should keep in mind, right? Pretty much everything we do in this class, we're kind of basing it on what's going on in one variable calculus and how things in one variable calculus works. All right, so let's look at, again, our two-variable function. Let's assume it has a critical point at AB, or a place where gradient f equals 0 at AB. Let's think about this. So I'm going to draw the domain. XY. Here's our point, A comma B. All right. And let's do what we said in the very, very beginning of this class. Let's take a direction. Let's call it U. And let me give it kind of coordinates U1I plus U2J. Okay. Let's assume it's a unit vector. All right. Just for convenience. But it doesn't really have to be, but let's just think of it as a unit vector, because at least our book's definition of directional derivative insists that things should be unit vectors. Okay, so let's say it's a unit vector. Now what we're going to do is we're going to do exactly what we talked about at the beginning of this section, or this lecture here. We're going to think about the function above this line, and we're going to look at how it curves, right, whether it's concave up or down, as a one variable function. All right, so let's actually calculate that, what the second derivative is of this composition function. Okay, all right, so in particular, I'm looking at x of t equals, I'm based at AB, so a plus u1t, y of t equals b plus u2t. That's my parameterization of this line. When t equals 0, I'm at a comma b, right? So I'm interested in what's going on at t equals 0. T equals 0 corresponds to AB. That's really important because I'm going to be plugging in, I want to plug in a comma b, which is equivalent to plugging in t equals 0. All right? Okay, So I want to look at, again, I want to look at the f as a one variable function above this line segment. So I'm going to be looking at f of x of t, comma y of t. And in particular, that's equal to f of a plus u1t, comma b plus u2t. Looks kind of terrible, but a is a constant, b is a constant, u1's a constant, u2's a constant. All right. So you can see it is a legit one variable function. Okay. All right. Now I'm thinking about second derivatives, and I'm thinking about what second derivatives can tell me about my function. So I'm going to take the second derivative of this guy right here, right? So I'm going to take d squared dt squared at t equals 0, because I'm interested in the point AB, of f of a plus u1t, comma b plus u2t. Okay? So this is literally what we did for the first derivative, right? That's how we understood how a function changes in a certain direction. Now we're calculating how a function curves, right? Concave up or concave down in a certain direction, all right? And again, we know that the first derivative is equal to 0 because we know that gradient of f at AB is equal to 0, right? So I should write that just as a quick reminder. Gradient f at AB equals 0 tells me that directional derivative in the direction u of f at AB equals 0, right? And that's literally d dt of f of x of t, y of t at t equals 0. That's equal to 0. All right, so I know the first derivative of this f is 0. So it's not that interesting in a way. So I'm taking the second derivative now. Okay. All right, so let's do this. This is a very nice exercise in the chain rule, in the multivariable chain rule. So this is equal to d dt of, and at t equals 0, I'll put in t equals 0 later maybe. So d dt of, I'm thinking whether I want to write everything. So I'm going to do this. T equals 0. I guess I'll do it now. So, okay, I'm going to do the chain rule. So f sub x, right? And then at the point of interest. So the problem here, what I'm kind of debating is how much I should write this inside, because it's going to get a little messy, right? F sub x at the point of interest, comma, dx dt, right? So this is df dx dx dt. What's dx dt? Well, x is a plus u1 t, right? So dx dt is just u1. And remember, u1 is just a constant. So this is f sub x, df dx, dx dt, which is just u1. All right? Just a constant u1. All right. And then plus, now f sub y, df dy, at the same point, a plus u1t, comma b plus u2t. And then times dy dt, y is b plus u2t, so times u2. Okay, and again, u2 is just a constant. All right. Now I want the second derivative, so I want to take d dt of this thing here, right? So let's do that. So again, it's the chain rule. We're going to take d of the first thing, f sub x, df sub x dx. So that's fxx, right? Now I'm gonna drop these inside stuff because it's gonna just look a little too messy. So fxx and then times u1. Just the u1 just carries over because it's just a constant. And then times times dx dt, right? So it's a derivative. Let me say it like this. It's a derivative of this with respect to x, which is fxx u1, and then times dx dt, which again is u1, right? So this is u1 squared here. Okay? Plus the chain rule of just this first term, right? When I differentiate it with a t, I'm going to have to take fxy as well, right? So the derivative of this term here with respect to y, so that's fxy, right? And then I still have the u1 coming along for the ride. and then dy dt, which is u2. All right. Okay, now both of these are evaluated at a plus u1t, b plus u2t at t equals 0. All right, I'll stick that in maybe later. Okay, plus, let me put this on the second row. The derivative of this second term with respect to x, so that's fyx u2, and then times dx dt. So it's derivative of that dt. So it's u1, oops, plus the derivative of this whole box with respect to y, so that's fyy u2, right? Just that u2 just comes along. And then the dy dt, which is again the derivative of the second term, input term, with respect to t, so that's u2, so u2 squared, all right? Okay, all of this is evaluated for my functions, this one, this one, this one, and this one is evaluated at a plus u1t, comma b plus u2t. But remember, I'm interested in t equals 0, right? And I've finished differentiating, so I'm allowed to plug in the t equals 0 here. So this is at t equals 0, right? So obviously, at t equals 0, all this business is just a comma b. Okay? So this is actually fxx at a comma b, u1 squared, plus fx, two of these, because notice that this term and that term are the same. And again, we can swap the order of the partial derivatives because we're assuming everything is nicely differentiable and all that. Okay, so this is plus 2 fxy ab u1 u2 plus fyy ab u squared. Okay. All right. Now, so what is this this terrible thing here? This guy here is the second derivative. Let me say it like this. It's how my function curves above this line at the point AB. Okay. All right. Looks terrible. In fact, it looks really, really terrible. However, we can actually simplify this really, really nicely. So if you know any linear algebra, take a look at this. fxx, fyy, all of this is at AB. fxy, this is a matrix, right? All at AB. Again, I want to emphasize the fxx, fyy, fxy, and fxy here. But I do want to stick in the ABs just as a reminder. This is just a constant number. Okay? All right. Times u1, u2. All right? That gives me a vector. But if I times a horizontal vector here, u1, u2, these two things are actually equal. So if you've done any sort of matrices before, these two are equal. All right? And you can literally just calculate it, right? This row times that column, the second row times that column gives you a column vector. And then now you multiply u1, u2. With that, you're going to get a number. What is that number? It's literally going to be this guy up here. Okay? All right, now, here's the important point. This guy here encodes, what we can see is this guy here encodes all the information about the second derivative, right? This guy here actually tells me how my function curves in the direction u, right? Because here is my u, right? u1, u2. So this guy right here, if I think about it in terms of vectors, that's my u, right? And this guy is u as well. And if we think about this, you know, in terms of linear algebra notation, this would be u transpose, but you don't have to worry about that. This is u, right? u1 comma u2 is u. u1 comma u2 is u, right? So this thing in here, so the u1 and u2s, these two guys in that bracket, my matrix, these guys are telling me what direction I'm interested in. And then when I stick in this matrix here and do the multiplication, that tells me how I'm curving in that particular direction, right? So if I wanted a different direction, I would use the same exact matrix, right? And I would multiply the different direction here and that same different direction here, right? 1 comma 3 here, 1 comma 3 here, or 4 comma 7 here, 4 comma 7 here. The matrix is the same no matter what. Okay, so in essence, this matrix encodes all the information about the second derivative, right? So one thing we can say at this point is the second derivative for two variable functions, and in fact for multivariable functions, should be thought of as a matrix, right? Just like the first derivative in multivariable calculus should be thought of as a vector, the gradient, in a way, right? So the second derivative should be thought of as a matrix. Okay, you don't see any of this in single variable calculus because everything is a number. F prime is a number, F double prime is a number. But now gradient F is a vector. The second derivative is a matrix. Okay. All right, and that matrix allows you to calculate how my function is curving in any direction super easily by doing a matrix multiplication. Okay. All right, where does the second derivative test come into this? Well, or at least the form that we saw. Well, the question is, right, or the thing is, let's say our function is a minimum, right? And so we expect if we put in any direction u1 comma u2, this guy is going to be positive, right? This expression right here, this matrix multiplication expression is going to be positive, right? Because if it's a minimum, it has to be concave up in every direction, right? Every linear direction. Okay, so what does that mean about the matrix? Well, that means that this matrix has positive eigenvalues. All right. If it's maximum, right, then you're always going to get minimum because it's a concave down in every direction. That means that this matrix has negative eigenvalues. Okay. If you have a saddle situation, that means there's one vector you can find, so one direction in which the function is kind of going downwards, right? And there's another direction where the function is going upwards, like that, right? What does that mean? That means there's a positive eigenvalue and there's a negative eigenvalue of this matrix. So the second derivative test actually should be stated this way. If gradient f of AB equals 0 and fxx, fyy, fxy, fyx, all of this at AB, 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 if this matrix has positive eigenvalues, then local min. All right. If it has negative, I should be more precise here, has all positive eigenvalues. There's two eigenvalues. So if they're both positive, then it's a local min. Has all negative eigenvalues. So there's two of them again. If they're both negative, then local max. Has one positive and one negative eigenvalue. Then saddle. All right. And if it has a 0 eigenvalue, at least one 0 eigenvalue, then we don't know. Right? It could be any case. It could be max, it could be min, could be a saddle. All right. Okay, so this is actually the proper way to think of the second derivative test, and this is the if so in some schools they do linear algebra before they do multivariable calculus, and if you did that, then this would be the version of the second derivative test that they would give. It wouldn't be the horrible one that we have, which is totally ad hoc, and it is that way because I guess they don't assume that people know, or we can't assume people know what eigenvalues are, right? Okay, so where does the expression that we talk about come from? Well, the one that we're talking about is we look at fxx, fyy minus fxy squared, right? All at AB, okay? So how does that relate to the matrix? Well, that's literally the determinant of the matrix, right? This is equal to determinant of fxx, fyy, fxy, fyx, okay? All right? And we know, if you've done linear algebra, you know that the determinant is the product of the eigenvalues. Right? And so what happens is, if you have two eigenvalues, lambda 1 and lambda 2, right? If they're both positive, right, then we're in the situation where fxx, fyy minus fxy squared is bigger than 0, right? So this is going to lead to our version of the second derivative test, right? If both of these are positive, then fxx fyy minus fxy is bigger than 0, because this would literally be lambda 1 times lambda 2, all right? And we're assuming both are positive, okay? All right. Well, if both are negative, then also fxx, fyy minus fxy squared is positive, right? So this is why you actually have to have this extra condition, because if both are positive, that means we have a minimum. If both are negative, that means we have a maximum. But yet, for both of those situations, the determinant is positive, because lambda 1 times lambda 2 is both positive in those cases, right? In one case, you're multiplying two positive things. In the other case, you're multiplying two negative things. So how do we actually differentiate between the two situations? Well, we look at fxx, because fxx, if we look at the matrix version of this, right? If I put 1, 0 and 1, 0 here, what am I going to get? I'm going to get fxx. Okay, that times that gives me fxx, that times that gives me fyx, and then that times that gives me fxx. So this is going to be fxx. But if you're a, let's say, a minimum, then this thing is going to be positive, right? So this thing is going to be positive. So if you're a minimum, in fact, like we said, no matter what I put here and here, and if I put the same things here and here, I'm going to get a positive number. So essentially, I'm saying that I know it's either both eigenvalues are positive or negative. I'm going to plug in one test case, and that test case is 1, 0. And if it turns out to be positive, then both eigenvalues have to be positive. If that test case happens to be negative, then both eigenvalues have to be negative. All right, because the sign has to be only one direction if we know it's a max or a min. All right. So this extra business here is testing whether both eigenvalues are positive or both are negative, right? In the case where they're the same sign, okay? If they're different signs, well, lambda 1 and lambda 2, one is positive, one is negative, then of course, this special quantity, this determinant of the matrix is going to be less than 0, because lambda 1 times lambda 2 is going to be less than 0, because one of them is positive, one of them is negative, right? And that's exactly, again, the situation where we have a saddle. And again, when the determinant is 0, that special quantity is 0, and we just know nothing. All right. Okay, so this is the correct version of the second derivative test. And again, if you haven't seen linear algebra, remember this, maybe refer back to this when you do take linear algebra and you learn about determinants and eigenvalues. Forget about determinants. Eigenvalues is the most important point here. And if you do know it, this is a much better point of view to take than the horrible, horrible one that we have in our class. All right. Oh, I guess I should say one thing. If you have taken linear algebra, you'll know that not every function. So I said this guy here is the product of our eigenvalues. But if you have taken linear algebra, you'll know that not every matrix has a full set of eigenvalues. So how do I know there's two? Well, the deal is if you have a symmetric matrix, there's always a full set of eigenvalues. This guy's symmetric, right? These two guys are equal to each other. fxy and fyx are equal. So it's a symmetric matrix. Symmetric matrices always have a full set of eigenvalues. Okay. All right, so everything is cool. So that's the second derivative test. You'll notice the book does not do a second derivative test for three variables because, well, look at how they had to twist and turn to get a second derivative test for two variable functions, right? It's not going to be easy to write down a condition for three variable functions that doesn't involve some sort of horrible expressions, right? However, with this point of view that we have in this discussion, I can tell you right now, it's super easy to write down a second derivative test for three variable functions. You would look at fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, fzz, and this should represent, and it does, represent how your function changes curves, right? Concave up or concave down in linear directions for a three variable function. And if you wanted to know exactly how it's curving in a particular direction, you do exactly the same thing. u1, u2, u3, u1, u2, u3. If this happens to be a positive number, then it means you're concave up in the direction u1, u2, u3. If it's negative, it's concave down, right? Same conclusions, right? So what's the second derivative test? It's exactly the same. If all three eigenvalues are positive, then you're a minimum. If all three eigenvalues are negative, then you're a maximum. If it's mixed, some positive, some negative, then you've got a saddle. And if it's zero, again, you don't know anything. All right? So super, super simple with this particular point of view. And so this is really good motivation for linear algebra, right? Why you care about linear algebra, even if perhaps you don't care about solving linear systems, okay? Which is, a big chunk of linear algebra. Okay, by the way, this matrix does have a full set of eigenvalues because it is symmetric. fxy, fyx, the same. fxz is equal to fzx, and fzy is equal to fyz. So there is three eigenvalues, so you can talk about all three of them being positive or negative or whatever, okay? And so, for variables, same idea. Any variables, same idea, because this is actually the proper way to think of the second derivative. Okay, we'll actually see this expression in the near future when we talk about integration. All right. I guess I should, as usual, I should say, all of this is happening at our point of interest. So this matrix here is just a number, right? At a comma b comma c, at a comma b comma c, and so on. All right. So there's nothing actually really fancy going on once you've set a point that you're interested in and a direction that you're interested in. Then it's just, the output of this quantity here, even though it looks maybe kind of mysterious, it's just a number. And that number tells you concave up or concave down. Okay. All right. So that's the second derivative test. In terms of our class, I'm going to treat it as a very, very minor topic. For this week, very, very much focus on optimization and 15.8, which is Lagrange multipliers, which is the next lecture. Oh, and I should always say, if you didn't understand this matrix business, it's absolutely fine. As long as you're able to use the version of the second derivative test that we gave for our class. Where is it? This absolutely disgusting one that we have over here. As long as you can use that, perfectly fine for our class. I'm never going to ask you something about matrices and stuff like that on our exam.